Simon's lecture, and today's title is An Analyst's Incursion into Perturbative Quantum Field Theory.
Okay, thanks. Yeah, so today's lecture is, so it's basically self-contained, so it will appear to have nothing to do with yesterday's lecture, and then we'll see tomorrow why it's really kind of the same. And so what I wanted to do is just show you an essentially self-contained piece of math, which sort of shows up actually in the context of perturbative Euclidean, if you want, quantum field theory, but you don't need to know anything about quantum field theory, so I'm not going to refer to quantum field theory at all. I will view it as a purely analytical problem. Okay? So in order to formulate the problem, I still need to introduce Primar diagrams here. Okay? And so what's a Primar diagram in this context? So it's basically a graph. Okay, so Primar diagrams. So it's an oriented graph. You're allowed to have multi-edges. In principle, you're allowed to have loops, but they can sometimes get killed automatically, so let's just not have loops. So that would be an example of such a graph. And now the graph has some additional pieces of data, so it has something called legs. So legs are basically half edges. So you can think of them as half edges, or you can just think of them as markings of vertices. Okay? But you could have more than one, so you can have two legs if you want to patch to the same vertex, that's allowed. The only condition is that, so your Feynman diagram doesn't necessarily need to be connected, so you can have different bits and pieces, but every bit and piece needs to have at least one leg. Okay, so there's no legless graphs if you want. And the legs are ordered, so you know that they have, there's the first one, second one, third one. Okay, so they are ordered. And furthermore, there's a bit of additional data attached to both the legs and the edges. We're going to just fix once and for all a dimension D, and we also fix some set of labels L. Okay, so L is just a finite set, so it's just some labels. And now to every edge, we attach one multi-index K and a label A. So K belongs to N to the D. So it's a D-dimensional multi-index. And A belongs to L. Okay, so in the A, we call it a type. Okay, so each edge has a type, the one, and it also has a multi-index like this attached to it. And each of the legs also has a Ki, say the ith leg has a multi-index Ki attached to it. So that guy also belongs to N to the D. Okay. Okay, so that piece of data is what we call a Feynman diagram. Okay, so let's write the capital gamma for a generic or Feynman diagram.
That's the leg orientation.
The legs don't, so the legs you can think of them as always pointing inwards. Okay, so in that sense you sort of fix the orientation.
You're not putting any labels on the vertices.
I do not put any labels on the vertices.
So all the vertices have the same kind of interaction.
No, so here, well, the interaction is just, okay. No, I don't put labels on the vertices, and the way it shows up, somehow I don't care.
I'd say time if put labels on the vertices.
Well, ordinarily, those labels would indicate particles, wouldn't it?
Okay, so here, if you want, these labels indicate the types of particles. Okay, so these that's the types of particles. But as I was saying, I want to view it as a purely math problem, and so I want no interpretation. If you want to interpret these things as particles, then certainly feel free, but
Let me rephrase it. Can the vertices depend on your case?
Can
The vertices have some dependence on your case?
No. So I mean, no, this K has nothing to do with a momentum. No, that's not a momentum. It's an element of N to the T. It's not an element of R. It's an index. It's not a momentum. Maybe I shouldn't have called it K. It's not a momentum.
What is the physics on here?
Sorry?
So what is K for physics?
So, okay.
Sorry, you have
Forget it for a second. So let me just now tell you. Right, so now, okay, just bear with me for 5 minutes, okay? So now what we really want to do, okay, so each of these Primar diagrams, okay, we want to view it as representing a distribution, okay? And it's a distribution in as many variables as it has legs. Okay, so here, and each space, if you want the underlying space, is always RD. And so here you view this guy as a distribution on R3D. Okay, so it's a distribution on 3 copies of RD because there are 3 legs. Okay. And how do you want to interpret it? Well, what you really want to do is you want to assign to each label, say A and L. So to each of these labels, you want to assign a kernel, Ka. Okay, and so Ka is a kernel, so it's just a function from Rd to R. And all these functions, we're always going to consider them as perfectly nice, smooth functions, compactly supported everything, except for singularity at the origin. Okay? So for the physicists, everything is in direct space, not in Fourier space. So ultraviolet problem is really at the origin. And for each of these guys, okay, so every element in L has a degree assigned to it. Okay, so we have a map, if you want, degree that goes from L into R plus. And what we impose is that the kernel Ka behaves essentially like it has a singularity at the origin, which has a strength which is at most that given by this degree. Okay? So Ka of x, or if you want any derivative, the kth derivative of K of x, we assume that it's bounded by x to the minus K minus degree of A.
Probably don't want to use
Okay.
K.
Sorry?
Probably don't want to use K.
But that K will be the same as that
it's the
K,
same.
and so that's on purpose that I wanted this K. So that's exactly what this K represents. And so now given, okay, so given the Feynman diagram, given such a kernel assignment, okay, so one kernel per type, that gives us a way of, gives us evaluation, if you want, and so evaluation is a way of assigning to each Feynman diagram a distribution in as many variables as there are legs. The distribution is always supposed to be translation invariant in the sense that if you translate all the variables by the same amount, you get the same distribution back. So it's really only if you want a function of, okay, it's not a function because it's a distribution, but you can just think of it as a function only of the differences of the arguments. Okay.
How do you use the multi-index of K?
Oh, well, because you see x is in Rd, and so so it tells you how many derivatives you take in each of the d directions. So, and then this just means you add up all the components. So yeah.
Sorry, again, make the rule contact equals You're dealing with your gauge theory, your gauge phase, and your refinement gauge.
Yeah, so there's no gauge. I mean, yeah. These things don't have, there's no additional in this.
In other words, your
scalar,
kernels,
everything is scalar.
your kernels are diagonal.
Scalar, yeah, everything is scalar.
Diagonal. You have no no mixed kernels, K, A, E.
No. Okay, so this guy is supposed to be a distribution. So I have to tell you how it acts on test functions. And the way you want to think about it is you integrate. So all of these vertices, you should think of them as being integration variables in RD. Okay, so you integrate over, say, RD to the power of your vertex set. And then for each edge, okay, so E is just your set of oriented edges. So every edge is oriented, so there's an E plus, which is sort of the target, and there's an E minus, which is the starting point of the edge. And so the corresponding edge E, so say if that's the edge E, it has an index KE and an AE here. Okay? And so what you take is you take the kernel AE, you differentiate it KE times, and you evaluate it at E plus minus E minus, or rather X E plus minus X E minus. And then for each leg, so you take your test function. Your test function is a function, you view it as a function of the variables that the legs are attached to. Okay, so let me call whatever. So I have n, say I have n legs, and so I have vertices, say v1 up to vn, which are the ones that the legs 1 to n are attached to. Okay, and so I take phi evaluated at x v1 up to x vn, but then each one of the legs has some multi-index as well, so I actually differentiate phi that many times in that direction, right? So here you take you differentiate the first variable kind of k1 times, etc., all the way up to the nth variable, where you differentiate kn times, and you integrate this whole thing over x. Okay? So whenever you're given these kernels, right, that gives you a way of turning a Primar diagram like this into a distribution by this form. Okay?
For different choices of K's, you have distributions.
For different choices of K's, I have different
So
distributions.
that your left-hand side should really be labeled at all those K's.
So the left-hand side, right? So this capital, so that's a capital K. Maybe I have too many K's in this business. So this capital K denotes, if you want, the kernel assignment. Okay.
The function sends A to K sub A.
Right, I understand, but you also want the labels for the little k, the k terms.
Yeah, well, they are all included in the gamma, right? Gamma is this whole piece of combinatorial, if you want to take it. Right? So gamma just is a shorthand for this whole piece of information, which contains the information about what's your vertex set, what's your edge set, what are all your k's, what are your a's, how many legs you have, and what are the indices sort of assigned to the different legs. Okay, so all this piece of information, gamma is just a shorthand for all this chunk of information. Okay?
I guess what I'm a little confused about the x e plus minus x e minus. You're not integrating, so this measured the x. Which variables?
So that's
All
all the
vertices.
xv's.
Not just the v1 up to v2. Okay.
No, it's all the, right? So that's the whole vertex set. Right? Every vertex has each vertex has one x attached to it. Whereas here, some of the, right, since you can have more than one leg attached to the same guy, so for example, it could be that V1 is equal to V2, just means that here you evaluate on the diagonal. Okay, so that's a lot.
As you said, I mean, everything just depends on the differences in
Right.
position, so you have one overall.
There's one overall somehow, yes. Which you could get rid of it, but I don't want to because that would make expressions horrible. The expressions are much nicer if you keep that. Okay. So what's the situation? So if you want to be a little bit more formal, let me write curly T, or say curly Tn for the free vector space generated by Primar diagrams with n legs. Okay, so it's the vector space generated by Primar diagrams with n legs. Okay, so just all formal linear combinations of Feynman diagrams with n legs. And I write curly T to be the direct sum over O n greater or equal to 0 of Tn, where n equal to 0 is there, but there is only one Feynman diagram with 0 legs, because I said that every connected component has to have at least one leg. There is one Feynman diagram with 0 legs, which is the empty one. Right, so the empty graph is a perfectly nice one, and it's all mapped to 1, like this. And, well, what's your target space? Write Sn to be the space of distributions, some translation invariant distributions.
You said you're not imposing that these are connected.
I do not impose that they are connected. Here it doesn't matter. Right? It just means that this whole integral factors into 2 bits.
Do you want your each connected piece to have at least one leg?
Yes.
Yes. So you
Yes.
rule out the
Yes.
bubble.
Yes. 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 So Sn is translation invariant distributions, Schwarz distributions, in, again, n variables. And, well, same thing, S, just the direct sum, n greater 0 of Sn. And so now this pi k, right, what we want here is a pi k, which is goes from T to S, which is an algebra homomorphism. Right, because there's a natural product of Feynman diagrams, which is just take 2 of them and put them together, right, view them as one, which you're allowed to do since it doesn't have to be connected, so you just view them as putting them next to each other. And there's a natural product on distributions where, if you have a distribution in k variables and a distribution in L variables, you can always take the tensor product, and that gives you a distribution in k plus L variables. Right? So there's a natural product here, which is simply concatenation of the diagrams. There's a natural product here, which is the sort of usual tensor product on distributions. Both of them are they are not quite commutative, right? Because here I said that it was important that the legs are actually ordered. So it makes a difference whether you put the first guy first and then the second guy, or the second guy first and then the other guy, because it makes a difference in the way you would order the legs. Right? You would either start counting from the legs of the first one and then go on to the second one, or the other way around. And the same for distributions. Right? If you make a distribution of 2 variables out of 2 distributions of 1 variable, you have to say which one is in the first variable and which one is in the second. Right? So it's not quite commutative, but it's sort of almost in the sense that, well, you have permutations acting on here that just shuffle the legs around, and you have permutations acting on here that just shuffle the arguments around, and you want this to be, you know, covariant under this action.
Could you repeat what S is?
Sorry?
What is Sn?
So Sn are just the distributions in n variables that are translation invariant, in the sense that if you take the test function, you translate every argument of the test function by the same amount, you get the same answer when you test the distribution against it. Okay? So the translation invariant in that sense. Okay? And so this guy, you want it to be an algebra homomorphism, you want it to be equivariant for the action of the permutations that shuffle arguments around. Okay? And now, okay, so what's the problem? So the problem is that in general, there's no reason for this integral to converge, right? Because I allow the kernels here to blow up arbitrarily. Right? I didn't actually put any restriction here on the degrees, so these kernels could blow up as badly as you want. There's no reason for them to be integrable. And actually, you can have more interesting kind of blow-up happening, even in situations where the kernels themselves actually happen to be integrable. Okay? So to show you so let me show you what kind of problem can show up. Okay, so let's take the simplest example. The simplest interesting example. Okay, so interesting example is the following. So take a Feynman diagram which has just 3 vertices, and okay, so if you want 3 legs. So take Feynman diagram like that. And I make all the k's equal to 0, so forget about the k's. And for the A, really the only important thing here is what the degree is. So I'm going to just write down the degrees. And so let's go in dimension 1. And so in dimension 1, a kernel is integrable if it blows up, well, with degree less than 1, right? So it has to blow up less badly than 1 over x to be integrable. So I can take, for example, 3/4. So I take a kernel. So I simply take here the function, my kernel, a function that has a singularity that goes like x to the 3/4 at small scale, x to the minus 3/4 at small scales. So each of these guys is perfectly integrable. Okay? But the claim is that this, I mean, if I look at the corresponding integral, that still actually diverges in general here. Okay, so let's see, why does it diverge? So what does this correspond to, right? So we're integrating, okay, so we have this test function phi, the k's are all 0, so there's no derivative here. So there's the test function phi. So let's take a test function which is equal to 1, somewhere in some neighborhood of the origin. So that means we forget about the test function. Okay, and so now let me just give these variables. So we have 3 integration variables. There's an x, y, z, and as you were saying, there's really one of them that I can kind of throw away, right? So I can essentially fix one of them, say x, and I just only consider the integral over the other 2. Right? So I have a dy dz. And then what's the integrand? The integrand is something like 1 over, there's an x minus y to the 3/4, y minus z to the 3/4, x minus z to the 3/4. Right? And say, I don't know, everything less than 1. So it's really a problem at small scales. So let's assume the kernels are sort of compactly supported. There's no problem at large scales. Okay? So now each of these guys separately sort of integral, but now let's estimate from below this integral in the following way. So I look at little regions. So I look at the region say, dn.
Wait, can you explain again, because maybe Martin understood this one, but I didn't. So, why is it that we can get rid of the last variable?
Because everything is only function of the differences,
Okay.
right? So I can introduce new variables that just parameterize the differences, and then somewhere there's one which is the sum, but this integral doesn't actually depend on that. So that would just be like the last argument of the test function, and so you just integrate over that first, you're done with that, and then everything just becomes an integral in one variable less. Right? And so then I can choose which one I want to fix, it doesn't matter. So I just fix one of them arbitrarily, right? And then the whole thing just becomes an integral as a remaining. Okay, so now I look at the region, which is basically the region where, say, x minus y is of order 2 to the minus n, and of order means not just bounded from above, but also from below. Okay, so really of order 2 to the minus n, say plus modulo factor 2 or something. And all of these distances are about the same. So I want x minus z to be of the same order and y minus z to be also of the same order. Okay, so all three distances are about 2 to the minus n. Okay. Now what's the volume of this region? Well, basically if two of these guys are of order 2 to the minus n, the third one is somehow automatically at least bounded from above by 2 to the minus n, and the bound from below doesn't really throw away all that much. So the size of that region is really basically, it's roughly a square of side length 2 to the minus n, so it's about 2 to the minus 2n, right? So the volume of Gn is about 2 to the minus 2n. But then, how big is the integrand on 2 to the on Dn? Right? Well, each of these guys is 2 to the minus n, okay? But they're on the denominator. So if I put them upstairs, so my integrand is about, well, 2 to the n to the power 3/4 plus 3/4 plus 3/4, which is 9/4. Right? Well, n times 9/4. And then you can choose these regions in such a way that they're all disjoint. And so my integral is certainly going to be bigger than the sum of, well, simply size of integral times, area over which the integrand gets integrated. And so this is certainly bigger than basically sum over n greater or equal to 0 of 2 to the 9/4 n minus 2n, but then there's still a quarter n left here, and so this obviously diverges. Right? So you see that even in situations where each kernel individually is integrable, it might be that this whole integral actually diverges. Right? So now what's the good condition that makes it converge? Well, the claim is that this is sharp. Okay, so that's a theorem which goes back to usually attributed to Weinberg, which basically says this argument is sharp. Okay, so that this is the only obstruction for this integral converging. And what does this mean? Okay, so when does this power counting here work? Right. So basically, what I'm claiming is that this kind of integral would converge provided the sum of these exponents here is strictly less than 2. Okay. And why 2? Well, because there were two integration variables. That's where the 2 comes from. Okay. And so the general condition is basically what you want. If you want to guarantee that this integral converges, well, then you would basically have to assume that for every subgraph of your graph, the sum of the exponents of these exponents in your subgraph is less than the number of integration variables, so if you want the number of vertices of the subgraph, -1. And the -1 being because of that 1 degree of freedom that you can always throw away somehow, right? The translation invariance. Okay?
This is again
So-
when the k's are all 0.
That's when the k's are all 0, and so of course if you have k's in the game, well then you just have to add them to your notion of degree. Right? So what this suggests is that there's a natural definition of, so let me write it just to make sure. So what it suggests is take any subgraph gamma bar of your Feynman diagram gamma, okay, so gamma is somehow your favorite Feynman diagram. You start it from, you take any subgraph. It doesn't matter whether you look at sort of complete subgraphs or not. And then I define the degree of a subgraph to be, and then of course, you have to do the power counting in the right way, in the sense that if the dimension were not 1 but d, then of course this here picks up a factor d, right? Your volume. So here you have a d times number of vertices minus 1, which was essentially this exponent here, right, the 2. And then minus sum over all edges in your subgraph of degree of the corresponding edge. And as you were saying, you have to add the value of k as well.
These have to be
Okay.
leggy subgraphs, I guess.
Sorry?
They have to be leggy subgraphs. They
No.
still have to have legs.
No,
They don't?
No.
Okay.
no, any subgraph. So the condition is now, okay, that the proposition, if for every gamma bar subgraph of gamma, degree of gamma bar is strictly positive, okay, then this integral here converges. Okay, and the proof is essentially given here. Okay, so it's just a slightly souped up version of this proof. You have to think a little bit harder, actually quite a bit harder, but what, in general, when you have more than just these, if you have this the full integral here, what's the good way of breaking it into regions of integrations? But then once you figure that out, the proof is essentially the same as that. So that's this Weinberg theorem, if you want. Okay? So it tells you if this kind of power counting condition is satisfied, so every subgraph has positive degree, then there's no problem, we know what this means. Okay? You can make refinements of this. For example, the problem here really comes from the region where all of these are very small. Right? So that means the region where all of these 3 points are very close to each other, if you think of them as being integration variables, right? So the problem really comes from when all 3 points sort of collapse to 1. And so this could, for example, be prevented. So suppose that the only divergent subgraph here is this triangle here. Okay? But then you test against the test function, which vanishes when these 2 arguments are close to each other. Right? And that means that these 3 points somehow never collapse. If they want to collapse, then the integral is 0 anyway, just because the test function is 0. Okay? And then you can prevent, if you want, that kind of law.
Is there a space of test functions that you can attach to these things so that it's always not going up?
Not necessarily, because for example, if this guy blows up, well, then you can't prevent that because you only have legs here, right? So basically, if every divergent, okay, so a subdiagram, if you want, is called divergent if the degree is negative, okay, for obvious reasons. And so if every divergent subdiagram is attached to at least two legs, okay, then you can find, you know, a big space of test functions for which that integral converges. Otherwise, you can't. Okay? And so now the question is, well, is there still a reasonable way of assigning a valuation pi k to an arbitrary kernel assignment here in a somewhat canonical way and which works for every finite die? So question, is there a natural valuation pi hat for every. So let me write curly k for the space of kernel assignments. And let's write curly k infinity for the space of those kernel assignments that actually happen to be smooth at the origin. Okay, here I only assume upper bounds, right? So nothing prevents that guy from actually being smooth around the origin, right? So if that guy happens to be smooth around the origin, if they all happen to be smooth, then of course again there's no problem in defining this integral, right? So what you want is you want the natural valuation for every kernel assignment in curly k, which extends sort of star continuously from curly k infinity, where it's clear what everything means, at least on data, say phi gamma, for which the star is guaranteed to converge. Right? So I just formally, I didn't really formalize it, but I sort of explained which test functions and which gammas would be such that this integral makes sense, whatever kernel we choose here, provided that it satisfies these bounds. Okay? And then what you want is you want a valuation so that for those gammas and phis, it coincides with that integral. Then for those where the integral is a priori not defined, well, it's something. Okay, so that's what you want to decide. But you also want to have it, so you want this to be somewhat canonical, and the way in which you make it canonical is you want it to be continuous in that argument on curly k.
With respect to this
With
weak topology.
Yeah, well, I mean, you see, this basically gives you a norm here, right? So you actually have a natural norm on that space, which is just the best constant here. So that's a natural norm. Okay? Right. And the point of the talk is to convince you in the remaining 20 minutes that the answer to the question is yes. So there is a natural way of extending this. And if you want, it's a generalization of the following construction. So take the super simple case. So the super simple case is the one in which you have a situation where instead of having like 3 kernels or something like this, you just have one kernel, which is not integrable. Right? So suppose you have just one kernel, which is not integrable. So you just have one kernel k. You can always turn that, there's a natural way of turning a kernel k into a distribution by saying k of phi is the integral of k of x phi of x dx, right? And now, of course, if the kernel has a singularity at the origin which is not integrable, then, well, it's not clear what that means. It is clear what it means if the test function happens to be supported away from the origin, because then again, there's no problem with that integral. Right? And so one way, for example, to make it always well-defined here would be to just subtract sufficiently many terms in the Taylor expansion of phi at the origin. Right? So if I subtract a sufficiently higher order Taylor expansion of phi at the origin, then I force the argument here to vanish at the origin to sufficiently high order that it cancels out the divergence of that guy. And of course, if my test function happens to be already supported away from the origin, then all these derivatives are zero, so I don't change anything. Right? So here there's a natural way of turning, any sort of kernel of prescribed singularity into an actual distribution by just doing it like this. Okay, and it has the property that whenever the original expression was guaranteed to have a meaning, I haven't actually modified anything. Okay? And so what we really want to do here is to make a construction of this type. But now what you also want is you want to keep as many properties of this valuation as possible. Okay? And so the natural thing to do first is to basically make a wish list of all the properties. Right? So if there are some algebraic properties that are satisfied by this guy, if there's some property satisfied by this guy, whatever the kernel assignment is, then you want to keep that property. Right? So whenever there are some exact identities that are satisfied for this guy, then you also want them to be satisfied for the renormalized guy, count K hat. Right? Because the idea is that what you really want to do is to use this guy as some sort of drop-in replacement for this guy here. And so you always want to think of that guy as having this meaning. And so whenever you guess some kind of identity from this formula here, you want that identity to be true for this guy. Okay? And so you want to basically go through, make a list of all things that are true for this guy. Okay? And then you want to make sure that that list, everything on that list is still true for this guy here. Okay, so what sort of things are true for this guy? Okay, so wish list. Okay, so the first item is what I already mentioned, is that we want to actually agree with that guy for the data for which that integral makes sense, right? So the first is we want to agree with the one pi k gamma of phi k hat should be equal to pi k gamma of phi for say gamma phi such that this is guaranteed to converge by Weinberg's theorem. Right, so for those pieces of data for which the assumptions of that proposition are satisfied, or somehow, if you want the souped up version of that proposition where you're also allowed to prevent collapse by having legs and choosing your test function the right way. So for all those guys, you don't want to change the definition. Right, so this we want. So that property is definitely one. So then, for example, well, there's one property which is you can, for example, delete a leg. So if you take a Feynman diagram, you delete one of the legs, okay? And then, so this guy now is tested against the test function that has one variable less. Well, that should be the same as the guy with the leg back tested against the test function, which happens to be constant in the direction of the leg that you've deleted, right? Because that's sort of obvious from this formula. Okay, and so we have a deletion operator which somehow deletes the last leg, except of course there's a little bit of a trickiness, which is that I said every connected component has to have at least one leg. Okay, so you might end up deleting a leg which creates a connected component that has no legs left. Well, in that case, you would want to just map that to 0 because such guys are not allowed. Okay? But now that gives you a map, del, that goes from somehow T to T, which simply deletes the last leg and maps it to 0 if you create a connected component without legs. And similarly, there's an operation, sort of iota, that goes from test functions to test functions, that makes a test function with one more variable out of one with one less by simply keeping it constant in that direction. And so then you want, I a hat of del gamma of phi to be I k hat gamma of phi. Okay, so that's simply formalizing what I just said. Okay, so that would be one property you want. Then another property you want is integration by parts. Right, so that's also one reason why I wanted to actually keep track of these indices separately, is that now I have a notion of derivation here on each vertex. Okay, so I have a notion of taking, here I can always just pick one of the variables and do an integration by parts. Right, by somehow putting a derivative on one, so throwing one of these derivatives on the other incoming edges. Okay. And so if you want, again, I have sort of like an algebraic notion of integration by parts here. And, well, integration by parts is not supposed to change the value of the integral. Right? And so what you have is, if you want, there's I have a dt, which is sort of the subspace of the guys that are 0 somehow for the integration by parts, right? So if I write down the integration by parts identity, I put everything to one side of the identity, so I get a subspace, which is supposed to be mapped to 0.
What do you mean algebraic notion of integration by parts here?
Well, you see, so you do, if you do an integration by parts on this kind of expression, you get again an expression of the same type, right? Which means that it actually comes from a slightly different Feynman diagram, and so I can kind of guess what integration by part means at this level. Right? And of course, at this level, it's just purely algebraic data. There's no analysis. So it's in that sense. So that gives me, so that's the guys that somehow get mapped to 0, simply because they would be linear combination of things that are equal under integration by parts. Right, and so what you want is that the I k hat gamma is equal to 0 for all gamma in this part. Right, that's somehow saying that integration by parts holds. And then there's another sort of property that you can do. There's a generalized notion of convolving two things, right? So here, there was a product which was simply putting Feynman diagrams next to each other, but there's also a convolution which you can take, which is somehow take the last leg of the first guy and the first leg of the second guy and simply glue them together at that location and delete the two legs. Okay? So that gives you a natural somehow convolution here. And, well, there's a corresponding operation of convolution between distributions.
But what orientation do you find?
Yeah, you have to fiddle around a little bit to get it right, but it's not a problem. Okay, so you want somehow convolution. Okay, so you want it to be correctly under convolution. And
What kind of type do you assign to the convolution?
sorry,
What kind of label, the L label, do you assign to the convoluted T-legs?
no, there's no, so they just get deleted, right? I mean, you see, so if I have one guy, a second guy, okay, so say it has sort of legs sticking out, this guy has legs sticking out, and now what you do is you simply attach, so you attach this vertex to this vertex, you don't create any new edge. You simply attach this vertex to this vertex and you delete the two legs. Okay? So you should think of the legs as being more like delta functions. You shouldn't think of them as being propagated. If you want to propagate it, you just add an edge and you put a leg at the end of that edge. Okay. Okay. So, yeah.
By doing so, you create a new type of vertex which didn't exist in
It's not quantum field.
the
It's analysis. I have put no restriction on what kind of vertices I have. Okay. So, okay.
But the title of this talk is perturbative convolution.
Hmm?
But the title of this talk is perturbative
All
convolution.
the time as an analyst, incursion into perturbative convolution. With the emphasis for an analyst. Okay. Right. So now how do we want to build this renormalized guy? Okay. Well, so if you think of what did we do in the case of just one kernel? So in the case of one kernel can be viewed as somehow if you want the trivial Feynman diagram, which is somehow something like this. Right? That's just one kernel. And then the way we modified it is we subtracted this kind of Taylor expansion of the test function at the origin. But evaluating the test function at the origin is really the even more trivial Feynman diagram, which is the one which has no kernel at all and just two legs. Right? Because here you simply, that corresponds to, if you want evaluating the test function on the diagonal, but there's always this one degree of freedom that you throw away. So the diagonal really means the origin of the transverse variable. And so what we've really done is we have actually subtracted from this guy what you get by, hitting this guy with the canonical valuation. And then, well, there were some additional derivatives, but the derivatives are also guys like that, just with additional label k's, right? Because the additional label k then hits the test function here, and so that gives you the derivatives of phi at the origin, right? So the natural thing here to do is to look for, right? So you want to look for maps M that go from curly T to curly T that map a Feynman diagram to some linear combination of Feynman diagrams with the property, well, and then you want to define such that you want pi km. So if you define a new pi k, so say pi k hat, as simply pi k composed with m, Right? So you look for all the linear maps M from T to T, which have the property that if you define a new valuation by simply composing the old one with M, the new one still satisfies all of these, the whole wish list. Okay? So this guy satisfies all the wish lists.
The K migrate up, that's just
Oh, the K migrated up? Yeah. Okay.
nine.
No, it's on the system. Okay, so so now you want two steps. So the first one is figure out what these maps are. Hopefully there's enough of them. Okay. So then we have sort of candidates. So that's first step. Second step is find, for every k, for every smooth k, you want to find a map mk of this type, and you want to find this in such a way that now if I define the pi k hat with this particular map, okay, so the pi k hat equals to pi k mk is continuous. Okay, so extends continuously to all of them for every Random diagram and every test function.
But you could have more than one such MK.
No. Well, almost. Yes. Yes, you have more than. No, actually, no. No, you don't. If you impose furthermore that you don't want the M to change the degree of, well, is it increase or lower? In one of the directions. You don't want it to lower the degree. Okay, so if you furthermore impose, right, there's a natural notion of degree. I've written down what the degree is. It got deleted somehow. Right, so it was a degree for sub-diagrams, but obviously there's the sub-diagram, which is the whole guy. So each of these guys has a has a degree associated to it. And so if you furthermore impose that M doesn't lower the degree, then the claim is that there exists exactly one M, which has both of these properties. So there's this property here, and we also make stuff M continuous. Actually, there's really just only one guy, which has this property. But that's actually slightly artificial. The reason, what makes it unique here is that it's slightly cheap. So is that, there was this leg deletion thing. And I said that if the leg deletion happens to create a connected component with no legs left, then I map it to 0. Okay? And that actually gives me the rigidity which makes the guy completely unique. I could also have said, well, I simply look at only guys which gets mapped to something where you still have at least one leg left. Right? And that would give me a little bit weaker condition here. And then, well, that would make this M not unique, but it would still make it exist. Okay? So, right, because what this means is that essentially those Feynman diagrams that have no legs left, which is the ones where you simply just integrate this whole thing without any test function formally, those guys get mapped to 0. And at least those with negative degree. That's what the leg deletion does. And well, that gives you some kind of rigidity. But okay, so if you forget about this, then the important thing is about the existence. Okay, so that so the claim is you can find an element, you can find a way of assigning an element here to each k, so that this guy becomes continuous in k on every Feynman diagram and every test function. And okay, so in the last 2 minutes, so let me just give you an idea of how this map looks like. Well, okay, so the claim is that the set of all such maps is actually a group. It has a nice group structure, which is, okay, not unreasonable. It's not completely obvious from the definition here. Okay, but the point is that if you have a map which, starting from the canonical guy, preserves the whole wish list, and actually you could start from any guy which has all of these properties, and you apply the map to it, you get again a guy with these properties. Okay, so you can compose these maps, you get a map of the same type, and they actually have inverses as well, which are of the same type. Okay, so the set of these maps is actually a nice group. And what do the elements look like? So how does the group act in these Feynman diagrams? Okay, so what's the typical action of an element of this group on the Feynman diagram? Well, you can almost guess it from what I explained to you of what happens with one kernel, right? With one kernel, what we see is the Feynman diagram corresponds to just one edge with two legs. And what we did is we actually simply removed the edge, we kind of contracted it, and then we kind of threw derivatives onto the two legs that are adjacent. And that's the same thing here. So what you do is you iterate over all divergent subgraphs, and you contract them to points. And then maybe you also somehow throw derivatives on the adjacent edges in a suitable way, which is sort of the analog of the Taylor expansion kind of thing that we saw. Okay? And so what you do is you really, an element of this group is simply a way of assigning a number to every divergent subgraph. Well, also a little bit more, but basically, so it's basically just assign a number to every divergent subgraph, and then the way this specific element acts on an arbitrary Feynman diagram is just iterate over all possible ways of finding some disjoint divergent subgraphs in your diagram and contract the connected components to points and pull out the number, which is the number associated to the corresponding graph. Okay, so if you want, it sort of looks like this. So you assign, so your MK is really determined by a bunch of constants, say CK, for every somehow divergent Feynman diagram, and then the way you act with MK on an arbitrary Feynman diagram is basically, I'm slightly cheating because this would correspond to somehow just keeping the first term in the Taylor expansion, okay, so the higher order terms. But the first term in the Taylor expansion would just be contract right? So you say, well, so the gamma bar might not be connected, but then if gamma bar is not connected, you want this to be multiplicative. Okay, so C of somehow a bunch of connected components is simply the product of these constants, so you really just assign a constant per connected component. And then what you do is you iterate over all divergent subgraphs, so you might have more than one connected component, and then you contract each connected component to a point, and you pull out the corresponding factor. Okay? And the claim is that you can find a bunch of constants C, Ck, which is, there's a formula for it, more or less explicit, but they're essentially characterized by this property that somehow this deletion operation gets mapped to 0 when you somehow delete the last leg, which basically means that those guys who are divergent by themselves, if you test them against a constant test function, you want to get 0. Okay? That's basically a property like this. You find the only constants that enforce that, and the claim is that they actually make that map then continuous. Okay. And of course, there was a bit of freedom because, well, these specific values make the map continuous, but you could just add 1 to the value and then it would still make it continuous, but it would be somehow much less canonical. Right? So there's basically only one canonical way of assigning these constants to any choice of. Okay, right? And so the point here is that the values of these constants are perfectly well defined for a smooth kernel. They blow up Right? They are not well defined for an arbitrary element here. Right? So when you want to extend this continuously to all curly k, these constants blow up, but that guy also blows up, and this combines it in exactly the way that makes this guy actually converge. Right? So I think I'll stop here for today. Thank you very much.
Are there any questions?
I'm sorry, what is the inverse of that
There's a recursive way of writing it down. I mean, you can, the way you would really formalize that, okay, so you can actually, okay. So you have a second space here, which is essentially the Primar diagrams without legs. Okay, and then you should really kind of think of each constant here as being indexed by a connected Primar diagram without legs. And then that space is, well, it's an algebra again, because you can just put them together, but it's also a co-algebra. And so with a formula like that, which gives you the co-product, and it actually makes it into a half algebra. And this formula here turns that guy into a co-modulo over that half algebra, and the inverse is just given by the antipode of that half algebra. Okay, so you just have a formula, there's a recursive formula for the antipode, which gives you the inverse. And in some sense, the formula which gives you this guy here is a formula which is somehow very similar to the formula for the antipode, the projection thrown in somewhere, and that's sort of what, like in this whole Primar business, what people call sometimes the twisted antipodes. And that gives you a kind of explicit formula for these constants.
In this language, is there an easy way to say what it means for theory to be renormalizable?
Here, no, because so this here was somehow a complete purely analytical statement, right? And so this continuity here is sort of always true. So then it's really more about, you see, when you then talk about, you don't want to look at all possible Feynman diagrams, you want to just look at these Feynman diagrams that are generated by your favorite Lagrangian muscle, right? And then you would say that it's renormalizable basically if this operation only creates new Feynman diagrams that are kind of generated by the same Lagrangian or fucking constants. And then maybe the tricky bit, you see the tricky bit is that then in some situations, which I didn't address here at all, in some situations, these constants, well, it may well be that there's additional structure that makes some of these constants actually vanish, or some of them be equal for non-trivial reasons, or things like that. Right? And so then you have somehow interesting things happening where you would think that maybe new terms are created, but actually they are not because of some difference in stuff.
And does it have in some sense to do with these constants being finite or something? Finite numbers of them or something?
Yeah, so, okay, so the sort of super renormalizable basically means that you only have finitely many constants showing up here. It's basically a finite dimensional subgroup of this big group that kind of does all the work for the collection of Feynman diagrams that you're considering.
So for your pi k without hat, is there like intrinsic way of explaining the formula? Like where does it come from?
Well, okay, so the thing is something very similar to this is, so what I'm going to explain tomorrow is a bit how this relates to the kind of stochastic PDEs that I showed yesterday. Right? And so in that context, what these K's here will be is basically the heat kernel. And so they really come from sort of the linearized evolution of these equations. So the Ks would be heat kernels or derivatives of the heat kernel, etc. Or they would be correlation functions of the noise. And so somehow if you take one of these SPDs I wrote down yesterday and you formally write down kind of perturbative series for it, and then you look at you try to compute the covariances of the terms that show up, then they have exactly that form. And they blow up for exactly that reason, for the same kind of reason.
Well, thank you very much.
Third and final talk is same place, same time tomorrow.